Well, thank you very much. It's a great pleasure and an honour to be here to give this lecture this evening. So chemistry's conflicting, complementary and contentious contributions to war and peace are symbolised really most conveniently for this evening's purposes by Fritz Haber and to a lesser extent by Alfred Nobel. Haber was an academic chemist who contributed enormously to industrial chemistry and is therefore a fitting mascot for this joint occasion. As the prime mover in the fixation of atmospheric nitrogen, thus standing at the head of the nitrogen stream that trickles down not only into fertilizers but into countless artifacts and pharmaceuticals, he was responsible for alleviating hunger and prolonging life. Yet he was also, as is well known, essentially the father of modern chemical weaponry, and thus responsible for using his left hand to bring death to those who with his right hand he had succoured. Nobel represents ambiguity of another kind. He too was responsible for a variety of developments in the general field of explosives, the invention of dynamite being the most famous, but other innovations too, and his fertile commercial mind, to some extent, is a summary of what is best in chemical industry, yet applied to killing, quarrying, and construction. His conscience, of course, led him to encourage the peaceful deployment of chemistry and other disciplines by the foundation of his prizes. And the sound of the clash of these two symbols of ambiguity was the fury directed at the award of the 1918 Chemistry Prize to Haber, which he collected in 1920. In 1918, Haber had been included in the list of war criminals, and his name does not appear in the list compiled in 1920, but outrage lingered on. Ambiguity. Let me dwell on that word. I wish in part to spin my talk from that word ambiguity this evening and to focus on the often ambiguous role of chemistry in war and peace. There's one feature, however, that I shall sweep from my presentation right from the beginning, which is the marvelous and unarguably positive contributions of chemistry to the modern world, entirely through the fruitful liaison of academe and industry, catalyzed by the invigorating spice of entrepreneurship. No one can doubt that chemistry has contributed profoundly to the comforts and opportunities of civilization, and specifically to the material infrastructure of the world. Strip away the contributions of chemistry, and we are literally back in the Stone Age. Eliminate chemistry now, and you eliminate the prospect of new technologies. Chemistry has changed the texture of the world. Where once it was iron and wood, it is now a rich variety of synthetic sensations. No one can doubt the extraordinary impact of chemistry on medicine, not only its curative contributions through pharmacology, but perhaps most important of all, its provision of anesthetics to dull the fangs of pain. Agriculture has been developed to sustain the overburdened planet, and through chemistry's manifestation in the form of molecular biology and genetic engineering, when allowed, will achieve even more in the face of ever more pressure from overpopulation. Transport, too, has taken us from animal muscle to space flight through chemistry's development and improvement of fuels. All that is so obvious that I don't wish to dwell on it, although I accept that in other contexts, such songs of praise are essential for the acceptance and propagation of our subject. No, I don't intend to dwell on the obvious. Instead, I shall dwell on the subtleties of ambiguity. Is it conceivable that good can come from chemistry's contribution to killing? As although my talk will now take a darker turn, we must never forget the extraordinary contributions that chemistry has made to the quality of life and to the enjoyment of peace. I'd also like to recognize that this is a talk before our joint chemical societies, so it needs some chemical edge. The other great contribution of chemistry has been to our understanding of the molecular infrastructure of the world, not just paeans of praise. When in times of peace we have time to reflect, chemistry provides insight into the beauty of the world by exposing its molecular mechanisms. I shall therefore also bring onto this stage a molecular understanding of some of the processes of warfare. Although the understanding cannot soften the impact of war, it at least adds to our comprehension of what happens when gases kill and maim, and through that understanding perhaps lead to the partial mitigation of its effects and even point to happier ways forward. Let's return to Haber, for he raises an important ethical point that it would be cowardice to evade. I shall begin with a remark he made in a lecture entitled Chemistry and War that he delivered at the Reichswehrministerium, the Ministry of Defense, to use that now almost universal Orwellian translation of Ministry of War, on the 11th of November 1920, when he said that gas weapons are definitely no more inhumane than flying bits of metal. Let's analyze that remark in the context of chemistry's contributions. It will be my theme this evening. First, that word inhumane. Why is chemical warfare regarded these days, if not by Haber, as more inhumane than what we might call physical warfare, using knives, spears, bullets, and bombs? That these entities all have a chemical dimension is something to which I shall return. Why is chemical warfare linked in repulsiveness with biological warfare, warfare conducted by the propagation of disease? Why is physical warfare more sporting, better cricket? Put another way, why is there an effective and properly lauded OPCW, Organisation for the Prohibition of Chemical Weapons, but not an effective OPPW, an Organisation for the Prohibition of Physical Weapons? All weapons, physical and chemical, maim. So the fact that chemical weapons maim is not the reason for the horror they induce. Chemical weapons inflict injury that persists for a lifetime. But physical weapons often remove limbs, and limblessness and similar personal invasions also last for a lifetime. Chemical weapons are said to induce a singularly painful and lingering form of death. But a bullet in the stomach is not a laugh a minute, and often longer. Chemical weapons are regarded as being indiscriminate, killing and maiming blindly. But the bombs that have been dropped by the megaton in wars gone by and going on still do not dismember only those in uniform. Indeed, although chemical weapons are regarded as a particularly nasty way of bringing death to an enemy, it's conceivable that one could be developed that brought that death in a gentle, sympathetic way. What would be our reaction then to a compound that smelled of lily of the valley, induced unconsciousness, and killed the insensate victim gently and peaceably? Would we find that repugnant or simply unsporting? Now, several factors point to differences between the effects of physical and chemical weapons. One is the persistence of the effects of some weapons, which deny access to certain terrains for months, like minefields, but much harder to remove. Then there's the psychological impact of such weapons, not only the fear that death might creep up on one unseen, but a visceral discomfort at the thought of being poisoned and subjected to a slow, agonizing death, in contrast to what is imagined as the quick scything of a bullet. There are, I think, fundamentally two reasons why there are institutions like OPCW. One is that, unlike a physical weapon, which can be used benignly, a chemical weapon is perceived as a single-purpose item, a weapon to kill and only kill. Conventional explosives have been used to quarry, mine, and build canals. Even guns can be regarded as providing protection and guarding sensitive installations. Nuclear weapons have engendered nuclear power. A chemical weapon, though, is perceived as having but one function, with no compensating use. I shall explore that perception later, but it is an important component of the distaste they induce. Like nuclear and biological weapons, chemical weapons are regarded of mass destruction. But I think there is a difference in the nature of the underlying fear. The underlying fear about nuclear weapons is that they represent mankind's ability to annihilate itself on a global scale. The underlying fear about chemical and biological weapons is more the prospect of debilitation and pain locally rather than globally. That fear is more personal than geopolitical. Now, the second fundamental reason for the existence of an OPCW and not an OPPW is purely pragmatic. Physical weapons have been with us since the first shaped flint was used to slay an opponent. Chemical weapons have been with us in the current meaning of the term only since the invention of industrialized war in the early 20th century, and as such can be scotched at birth. Nuclear weapons, also late to the party, are similarly open to control. Back to my theme. I shall move on to another feature inspired by Haber's remark that gas weapons are definitely no more inhumane than flying bits of metal, and distill from it a little chemistry. Those flying bits of metal, their bullets and shells, are impelled by explosives that chemistry has striven to perfect. About 1,000 years ago came gunpowder, that black powder mixture of charcoal, sulfur, and potassium nitrate. Gunpowder probably originated in China in the 9th or 10th century under the Tang, with the materials being perceived as so important that the emperor banned the sale of sulfur and potassium nitrate to foreigners, much like the sale of weapons-grade uranium and the constituents of chemical weapons are controlled today. Then the Chinese army had to defend itself against the Mongol hordes. But trade is a leaky business, and knowledge, however secret, is contagious. and in due course the secret of its composition reached the West, is epitomized by that necromancer and putative father of science, Dr. Mirabilis, or Roger Bacon, in the mid-13th century. Gunpowder survived as an important explosive for centuries into the middle of the 19th century, largely on account of its mediocrity. Mediocrity is a valuable attribute, as any chemist knows from a moment's glance at the periodic table. Even that sometimes wise Handbook of Life, the Bible, recognized it in its assertion that the meek shall inherit the earth. Thus carbon, one of the meekest of elements, almost literally mediocre. I had to look up the etymology of mediocre. It comes from the Latin for halfway up a mountain. So carbon lies between the vigorous, halfway up the mountain really, between the vigorous alkali metals on the left of the table and the vigorous halogens on the right, and so casual and undemanding in its nature that it is content to bond to itself. Inherits, if not the earth, then the entire biosphere, through the abundance and complexity of the compounds it forms, and even culminates in being able to reflect upon its own mediocrity. Thus gunpowder, a relatively meek explosive, inherited the earth of armaments, for it is a low explosive. It is only a crude mixture of fuel, the charcoal and the sulfur, and the oxidizing agent, the potassium nitrate, and so explodes in a rather lazy way. As such, it propels a projectile smoothly along a barrel rather than exploding violently in the breech. A high explosive imparts a short, sharp shock and so destroys rather than impels. And one lasting social consequence of the development of long-lasting deployment of gunpowder for use in firearms was the emergence of standing armies. When bows and arrows, swords and spears were the weapons of choice, a rabble could easily be raised by a baron with little notice and less training. When firearms became the norm, the technicalities of their use were such that a professional force had to be sustained. The immensely technical arena of modern armies is a direct consequence of the invention and slow improvement of gunpowder. If I now jump through 1,000 years to Haber again, then the use of potassium nitrate as an oxidizing agent had further consequences of the greatest significance for war and peace. Potassium nitrate was in short supply for war on an industrial scale, and other sources of nitrates had to be found. That search famously led to the arid uplands of Chile and the caliche. There are two problems with Chile and caliche, Chilean saltpeter. One is that it is largely sodium nitrate, not potassium nitrate. The sodium salt is moisture absorbing, and so cannot be used in gunpowder, which would become damp. Therefore, it had to be converted to the potassium salt. That could be done only on a small scale, so long as the only sources of potassium salts were wood ash and seaweed. But the conversion became commercially viable once the large deposits of potassium chloride, as carnallite, were discovered in Strasfurt in Germany. The resulting gunpowder was then used in the Crimea. The second problem was more substantial. The shortage of supply and the vulnerability of the sea routes from faraway Chile. These problems were responsible for Haber's development, together with the chemical engineer Karl Busch, of the catalytic synthesis of ammonia and the so-called fixation, but better, the chemical liberation of largely inert but extraordinarily abundant and freely available atmospheric nitrogen. Once ammonia was available, it could be oxidized to nitric acid and thus used to generate nitrates galore. The fundamental problem with gunpowder, the root of its low explosive character, but consequent pregnant mediocrity is that the oxidizing agent and the fuel are present in a simple granular mixture. High explosive character could be achieved by increasing the intimacy of the oxidizing agent and the fuel. The ultimate intimacy is achieved when the oxygen atoms are neighbors of the fuel atoms within the same molecule, and that is the nature of all modern explosives. The grandfather of these high explosives is nitroglycerin, the first of the compounds to displace gunpowder from its throne. That brings us back to Alfred Nobel and his series of inventions that included the taming of this ferocious liquid by absorbing it on kieselguhr, a diatomaceous earth, to form dynamite. Equally famous is nitroglycerin, as famous as nitroglycerin is TNT, with the juxtaposed of the oxidizing and the oxidizable, with a detonating shock encouraging the molecule to flex and bend and fall apart into little gaseous molecules that expands instantly to give the sharp impulse of destruction. Modern high explosives also include that favorite of the terrorists, Semtex, built around pentaerythritol tetranitrate and now rendered more readily detectable by various volatile additives. A feature that will not have escaped your attention is the presence of nitrogen in all the high explosives. The presence of oxygen is easy to understand, insofar as it is an oxidizing agent. But why nitrogen? I think, and I'm not sure of this, I think the answer lies in two aspects of the generation of nitrogen gas as a fragmentation product. First, nitrogen atoms form the very stable diatomic nitrogen molecule, N2, whereas carbon forms, among other molecules, the triatomic CO2 molecule. That means that the presence of nitrogen gives a lot of gas molecules per explosive molecule, and hence a strong shattering blow. Technically, the presence of nitrogen enhances the brisance, the shattering power of the explosion. The second related point is that the formation of triply bonded nitrogen molecules from individual nitrogen atoms is highly exothermic, and that release of energy adds power to the explosion. Now, I promised to refer to positive aspects of whatever I was talking about, because I wanted to emphasize ambiguity. Explosives, of course, have many peaceful uses, ranging from quarrying and mining up to some of the greatest earth-moving enterprises on the planet, as in the construction of the Corinth Canal and the Panama Canal. Rocket engines are essentially shells that have embedded motors and use what could be regarded as low explosives. The booster rockets of the space shuttles, for instance, were fueled by aluminium and oxidized by ammonium perchlorate, with iron oxide as a catalyst, bound together with a polymeric material and an epoxy curing agent. Nobel himself experienced the ambiguity of nitroglycerin as a killer and a life prolonger, for he was treated with it to alleviate his heart condition shortly before his death in 1896. The medical action of nitroglycerin is the treatment of angina pectoris, ischemic heart disease, is as a vasodilator, a widener of blood vessels, thus permitting a better flow of blood to the heart. And the chemical mechanism of the action is the conversion of nitroglycerin to nitric oxide, NO, a potent chemical messenger and vasodilator. Think Viagra, which acts by maintaining a lot of nitric oxide and through a mechanism that is well understood to increase blood flow. Not sure that nitroglycerin added to the mix would be welcome. I'd now like to turn from chemistry's contribution to the development of explosives to consider that other concept touched on by Haber's remark that gas weapons are definitely no more inhumane than flying bits of metal. I shall now consider the gas weapons that he brought into the theatre of war, but enlarge the concept to modern chemical weapons, which are typically not gases but viscous, clinging liquids. I shall show you why they are so nasty, indeed, contrary to Haber's opinion, inhumane, but that amid all that nastiness there sometimes glitters a positive good. That ambiguity again that I've been striving to emphasize, but not to overemphasize. For I do not know how to judge the balance of many saved lives against even a single lost or damaged life. If we disregard the poisoned arrows in the Amazon, but to which I shall return, then chlorine, cheap and less than cheerful, came first, and under Haber's direction was simply pumped across the battlefield in the general direction of the enemy. That primitive procedure was subject to the vagaries of the weather, and local nuisance of an errant wind might turn the scorpion on its tail. More sophisticated were the mustards. I shall spend a few moments talking about the infamous sulfur mustards, more familiarly mustard gas, and their cousins, the less familiar nitrogen mustards. They're so called because they smell like various mustard plants, such as garlic and horseradish. Incidentally, you might sometimes see the so-called NFPA 704 fire diamond. That's the US National Fire Protection Association fire diamond, a summary of hazards. And I shall affix the symbol to the illustrations I use when appropriate. As you'll see later, sulfur mustard scores high as a health hazard. What a surprise. The 4 signifying that it has that even a very short exposure could cause death or major residual injury. I'll return to the 1s later. It signifies that they are not very flammable and are reasonably stable under normal conditions. The sulfur mustards are also classified by OPCW as belonging to the Schedule 1. That is, as substances with no application other than as dealers of chemical death. I can't resist at this point introducing just a little ironical coincidence into the discussion concerning the structure of this fire diamond, for the colours are of the principal elements associated with the aspects of life and death. Indeed, if the spare square is regarded as phosphorus, then the diamond effectively summarizes all I shall be saying in terms of the elements. And after a 45-degree rotation, going to be seen to be a little fragment of the periodic table. Let's get back to inhumanity. Sulfur mustard is an especially vindictive weapon, for it operates at 2 levels and is lipophilic. That is, it dissolves readily in fat. That latter property means that it penetrates clothes and dissolves on contact with the skin. So avoiding breathing it by wearing a respirator is dangerously and misleadingly ineffective, and symptoms might start to appear many hours after exposure. The first level of attack is effectively chemical burning, leading to the formation of blisters full of yellow fluid. There are plenty of pictures like this on the web. I decided not to show more than one. Any inhaled vapor attacks the respiratory system, causing similar blistering and damaging mucous membranes. Now, the second level of attack might lie undetected, for the mustards attack the DNA of the victim and can initiate cancers. The mechanism of this secondary long-term debilitating attack is chemically very interesting, for it shows why the presence of sulfur in the molecule is essential for its action, just as nitrogen unexpectedly played a role in explosives. Moreover, the mechanism takes into that promised land of ambiguity. Thus, even untrustworthy sulfur atoms can turn on its neighbour chlorine and drive it out of the molecule, forming a potent triangular sulfonium ion. Its positive charge immediately attracts a lone pair of electrons from one of the bases that contribute to the double helix of DNA, specifically the pair belonging to the NH2 group of a guanine base, one of the 4 letters of the DNA code, and attached to it. The DNA has lost some of its function and can cascade into an uncontrolled replication that we call cancer. Where is the possible good news buried in this account? For a hint of that, we need to turn to the nitrogen mustards, where an NH group takes the place of the sulfur atom. These are Schedule 1 materials that act similarly to the sulfur mustards, causing initial blistering and later acting on the DNA of the victim who had escaped immediate death. They were stockpiled during the World War II, but apparently never used in anger. The glimmer of good in them is that, in principle, they can be used as cytotoxic therapeutic agents to stop the uncontrolled replication of runaway cancer cells. Thus, the loss of one chlorine atom and the attack on a guanine base forms one link, just like the action of the sulfur mustard. But the attack can be followed by a similar attack on the other end of the molecule, on the guanine base of the second strand of DNA, double helix, so binding them together and preventing their unwanted replication. One advantage of the nitrogen mustards over the sulfur mustards is that the H atom on the nitrogen is open to modification, but it is absent from sulfur. And that modification can result in a variety of types of control over the potency and possible side effects of the drug. Thus, the first nitrogen mustard to be used was mustine, in which the hydrogen atom is replaced by a CH3 group. Chemists can tinker much more elaborately, though, and bendamustine is one of their elaborations, and it is sometimes given to treat chronic lymphocytic leukemia and non-Hodgkin lymphoma. That's a depressing fact, I think, that some chemists are content to work on the development of superior ways of inflicting debilitating illness and death. Some, of course, are just obeying orders. Others, no doubt, rationalize their involvement in this horrid trade by taking the arguably legitimate view that it is necessary to know one's enemy and to study the effects better to protect the potential victim. But I'm not aware of a study of the psychological impact of knowing that one had contributed to a program, however benignly articulated, that so easily slips from deterrence to deployment, and which is similar to the study of those whose consciences got the better of them after working on various aspects of nuclear weapons during the 1940s. Be that as it may, chemical warfare moved on from obnoxious and debilitating vesicant, blister-forming mustards, which attacked the body, and turned its attention, as I now shall, to the destruction of the human soul, or at least the nervous system that permeates and inspires our very being. Nerve agents include a variety of phosphorus-containing compounds that fall broadly into 2 classes, the non-persistent G series and the persistent V series. The G stands for German, can't get away from it, the country where they originated. The origin of the V is obscure. It might be viscous, but other sources suggest that it might denote an aspiration to victory. The G series include tabun, first synthesized in 1936, and sarin, GB, which came along in 1938 or 1939, and is 10 times more effective than tabun. Incidentally, sarin is so called because it's an acronym formed from the initial letters of its discoverers. The V series emerged from research at ICI on organophosphate pesticides and includes VX, one of the most potent versions developed at Porton Down. The military advantage of the V series is that their persistency, their slow degradation, once dispersed over a battlefield, renders certain terrains inaccessible to the motion of the enemy, and so that motion can be controlled. The symptoms of both series, both G and V, include the usual list of horrors, descending from a runny nose through vomiting, urination and defecation, and ending, no doubt, mercifully with asphyxiation. But asphyxiation brought about not by the paralysis of muscles, by the excessive activity of the neuromuscular junction of the diaphragm. The agents kill by stimulating overexertion. Watching a fly die by vigorous swooping, buzzing and climbing after it has been sprayed by, to us, more benign killer agent gives a hint of what's going on. We need to step back a little and understand how a signal along a nerve is translated into muscular action. When an electrical impulse arrives at a synapse, the neurotransmitter acetylcholine is released, travels across that gap between the presynaptic junction and the postsynaptic junction, and stimulates action of the muscle. Its job done, the enzyme acetylcholine esterase, and watch that hole in the middle, that's going to be important in a moment, gobbles up, more formally, hydrolyzes the acetylcholine, and the muscle stops firing and relaxes. A nerve agent inhibits the action of the enzyme so that the acetylcholine is not removed. The muscle does not relax, and its contractions do not stop. It's not only muscles that don't stop contracting. Glands, too, continue to release their contents, and the victim effectively dies by drooling. At a molecular level, the nerve agent plugs that little hole that leads into the active site of the enzyme, and the acetylcholine cannot get into it and undergo hydrolysis. From a chemist's point of view, the battlefield where nerve agents are deployed contracts from the human landscape down to the neuromuscular junction, the link between signals from the central nervous system to the muscle that obeys the brain's command, where thought, including unconscious thought, is converted into action. To understand that microscopic battlefield, we need to know a little about what happens when a signal, an electrical impulse, arrives at the junction. When the pulse arrives, channels open that permit the influx of calcium ions into the neuron. These ions cause the vesicles that contain the neurotransmitter acetylcholine to fuse to the cell membrane, open, and let loose their contents into that synaptic cleft. The acetylcholine so produced floods across the cleft and attaches to receptors on the muscle fibre at the bottom of the slide. The effect of the binding is to open channels in the membrane that allows sodium ions to flow into the muscle cell and potassium ions to flow out. These migrations occur at different rates, with more of the smaller sodium ions entering than the potassium ions are escaping. So an electrical potential difference arises across the muscle membrane, the lower part of the illustration. And thus a signal begins for the muscle to contract. The affixation of the acetylcholine to the membrane is not permanent. It detaches, it drifts back into the synaptic cleft and is degraded into acetyl groups and choline by the action of the enzyme acetylcholine. The choline migrates back into the presynaptic terminal, where further biochemical processes convert it back into acetylcholine, ready for your next thought. Now, as you can see from this account, there are three principal soft points to attack. The One is the release of acetylcholine, another is its attachment to the postsynaptic membrane, and the third is the processes that occur in the cleft itself. All the military nerve agents identify the third possibility as the soft underbelly of the neuromuscular junction and focus on the role of the enzyme acetylcholinesterase. However, the two other soft underbellies of the neuromuscular junction also provide opportunities for chemical attack on the release and attachment of acetylcholine itself. In fact, what could be regarded as the first agent of chemical warfare, predating Haber's initiative by centuries, is the use of curare by the South and Central American Indians. Curare is extracted from the plant Strychnos toxifera, and the active component blocks the acetylcholine receptors on the muscle membrane of the postsynaptic cleft. As a result, the muscle does not respond to signals along the nerve, breathing ceases, and the victim suffocates. One antidote is to increase the concentration of acetylcholine by inhibiting the action of acetylcholinesterase, just as the nerve agents do. So here we see how one form of chemical warfare can mitigate the effects of another. Once again, there are ambiguities afoot. For curare, by preventing muscles to respond to orders, is an effective muscle relaxant and consequently has applications in surgery, for relaxation is decoupled from sedation. There's another aspect of chemical warfare, but of more trivial and cosmetic form, that of the war on wrinkles. Botox attacks the other soft underbelly of the synapse, the release of acetylcholine into the synaptic gap. I need to step back a little and lighten my tone a little in this largely grim account of chemistry's darker side and introduce you to the role of sausages in the war waged against wrinkles. Bacterium that is found on underprocessed processed food is Clostridium Botulinum, which causes botulism. The Clostridium part of the name comes from the Greek for spindle, and botulinum comes from the Latin botulus, for sausage, and refers to the danger of eating tainted sausages. Botulism, indeed, used to be called sausage disease. Botulism begins with facial paralysis, as some of you might know, and respiratory failure. The facial paralysis is sought in cosmetic applications as it eliminates wrinkles. And through a chemist's eyes, the active component of what goes on by the trade name of Botox is a reasonably big protein consisting of two components joined by a disulfide bridge. The smaller component, top right there, is the agent of action, and when it is present, it prevents the vesicles of the presynaptic terminal fusing to the membrane and releasing acetylcholine into the cleft. Once again, the muscles do not respond to the nerve's commands as the agent of transmission. Acetylcholine is now absent. Now, in the final part, I've got to stop soon, have I? Go on. In the final hour or so of my talk, I'd like to talk about control and elimination. Amid all the aggression that has marked history and currently geography, I think we can all discern a glint of hope for the future of mankind. We scientists are optimists. The development of weapons of mass destruction, be they chemical, biological, or nuclear, and the recognition that they represent a threat to all civilization, has led for the first time in history, really, to the prospect of their elimination, or at least their outlawing. In passing, perhaps it's appropriate to mention that in addition to these now almost conventional weapons of mass destruction, there is emerging the prospect of what might be called mathematical WMDs, with the prospect of attacks on the lifeblood of modern society, namely information. Is it conceivable that there will emerge an international consensus on its control, an organisation for the prohibition of mathematical weapons. Information is fast becoming the mainstay of society, with just about everything, including the security forces, as well as the economy and power and food distribution, depending on it. We've already seen hints of what a mathematical WMD can achieve in the Stuxnet, a computer worm that was directed specifically at Siemens' supervisory control and data acquisition systems that are configured to monitor and control specific industrial installations. The name of the worm is slightly obscure, but it seems to be taken from some keywords such as .stub and amrxnet.sys in the software. My concern here today, though, is solely on chemical weapons and the gratifying emergence of consensus that, with a certain national emissions, they should be banned. International agreement on the limitation of use of chemical weapons of various kinds goes back to 1675, when Germany and France agreed not to use poisoned bullets. Modern treaties really stem from an agreement 2 centuries later with the Brussels Convention on the Law and Customs of War in 1874, which prohibited the employment of poison or poisoned weapons and the use of arms, projectiles or materiel to cause unnecessary suffering. But a fat lot of good that did, for together with its successors in 1899 and 1907, based on The Hague, which purported to prohibit chemical weapons, but in fact oversaw their deployment on an industrial scale in World War I. No doubt, as a result of experiencing directly the horrors that chemical warfare engenders in practice in gas-filled trenches, rather than by abstract considerations in smoke-filled rooms, matters moved on with the Geneva Protocol in 1925, which prohibited the use of chemical and biological weapons in warfare, but did not ban their possession. Moreover, it left loopholes for their deployment should a non-signatory launch an attack. In due course, and I have no intention of going through the detailed diplomacy of its evolution, there emerged the Chemical Weapons Convention in 1993, which came into force in 1997. The convention imposes a legally binding worldwide ban on the production, stockpiling and use of chemical weapons and their precursors. Notwithstanding, there remain large stockpiles, the usual justification being that they are a precaution against possible use by an aggressor, or, like whale hunting in Japan, are needed for scientific research. There's currently 190 signatories to the convention, Syria being the most recent to accede, with a few alarming exceptions. Thus, Israel and Myanmar, Burma, are signatories but have not ratified the treaty and so are not bound by its requirements. States that have neither signed nor acceded include North Korea, with South Korea no doubt watching its unpredictable northern neighbour, with whom it remains formally at war, with understandably cautious apprehension. Now, the elimination of chemical weapons presents a variety of challenges. Even the elimination of them at source through their prohibition is not entirely clear-cut, because although some are single-use killers, like the mustards and VX, others can be made from chemicals that are reasonably readily available. Indeed, some nerve agents are made while the shell delivering them is actually in flight. That is, there is a distinction between unitary and binary weapons. The former consists of the nerve agent itself, the second of its precursors. For instance, it's easy to generate sarin in situ by the reaction between that compound and isopropanol in the presence of an amine to eliminate the hydrogen fluoride byproduct. Some of these reactions are frighteningly simple, and the fear is that terrorists and extremists in general can easily produce them with minor demands on laboratory expertise and equipment, as in the Matsumoto incident in 1994 and the Tokyo subway incident in 1995, when members of the apocalyptic Our Machine Cure religious sect, the name translates approximately as Supreme Truth, released sarin at a number of locations. It's for reasons like this that OPCW has devised 3 schedules for identifying actual and potential lethal compounds. I don't have time to go into them. Naturally, evasion occurs and stockpiles are discovered either voluntarily or by inspection, as we've seen recently with Syria, but in numerous other countries where, for one reason or another, quantities linger. The question then arises as to how the stocks may be destroyed. Schedule 3 materials might well find a legitimate home, as they include materials that are already used commercially. Schedule 1 and 2 are typically incinerated or hydrolyzed, such as by heating with concentrated sodium hydroxide. These procedures are infinitely superior to the previous practice of dumping shells and other active weapons at sea and hoping for the best. Such, for example, was Operation Chase, an acronym of cut holes and sink 'em, that consisted of filling a ship with old munitions and scuttling them in deep water. The USA alone seems to have dumped about 300,000 tons of the stuff in locations that it seems to have largely forgotten. The chemical weapons stockpiled by Libya have been destroyed in an operation that has been carried out much more discreetly than the current Syrian operation. Libya, which acceded to the Chemical Weapons Convention in 2004, had 25 tons of sulfur mustard, nearly 1,400 tons of these precursor chemicals, and more than 3,500 bombs containing chemical agents. In 2011, another 2 tons of mustard agent in artillery shells was discovered. All apparently have been destroyed by using special transportable incinerators built in Sweden, operated by Libyans and funded by the United States. And the current incomplete effort to eradicate Syria's stockpile is centered on the American cargo ship Cape Ray. Land-based procedures were considered, but no country was willing to offer hospitality. The cargo holds of the vessel are fitted out with 2 titanium-lined hydrolysis units, the so-called field deployable hydrolysis systems that use sodium hydroxide, sodium hypochlorite, and heat to convert chemical agents into conventionally hazardous waste. The procedure, which is designed to deal with about 50 tons a day, will be carried out in international waters. The effluent, about 500 tons of it, will not be discharged at sea, it is said, but treated as ordinary hazardous commercial waste. So watch out. I must conclude, I realise that, and rather regret having spent so much time on chemistry's destructive contributions to society. But I did warn you that would be the case. That when possible, I would underline the ambiguities of this dreadful application of knowledge, seeing glimmerings of light among the evil dark. Every branch of human knowledge and endeavour has lurking evil, as Pandora discovered. But the light generally, in my view, overwhelms the dark. And then justify it in ending on a positive note. If we stand back from the dark corner of our subject, and as we must, keep our vision of chemistry in proportion, then there's brilliant radiance, the unquestionable radiance of improved and lengthened life, and really the joyful radiance of burgeoning understanding. Thank you very much.
Returning to the start of your talk, you mentioned the unfairness of the perception of chemical weapons opposite, for example, mechanical and physical types. But do you think that's due to the invisibility of its action? And we've all seen explosions on Guy Fawkes nights. We've all shot bows and arrows and so on.
Well,
but it's in the insidiousness of the...
I did touch on that in the sense that one of the components of fear is that they creep up on you unseen, largely unseen, and sort of creep into your bed at night, as it were, and slay you while you slumber. I think that is a major part of their fear. The other part of the fear, of course, is the manifest type of injury that is caused. You see people really with their skin stripped off, and you don't want to see that. Happens also in, with conventional physical warfare, but it's associated with chemical warfare particularly.
Well, whilst we're waiting for another question, one of the striking things about your lecture is that the negative aspects of chemistry is always used on a large scale. The positive aspects used in medicine is minute. Is there anything in the agreements that people sign about chemical weapons which would prevent them making on a small scale the chemicals that would be used in medicine?
Well, I mean, you touched on a very important point, the ability to generate large amounts by small scale and easily hidden procedures. You know, a tiny pot in a garage in some country could go on churning out VX for years until there was enough for destruction never to be detected until it was used. And this is a serious danger. I suppose the same procedures really can be used for the generation of pharmaceuticals as well. And the day might come, I mean, if you look really forward into the way that manufacturing might be overtaken by 3D printing, then just as you can generate physical artifacts, largely of a useless application, in the future you might be able to generate chemistry sets, as it were, and indeed to build your own pharmaceuticals at home in them on a very small scale. So who knows? Yeah. So everyone will have a 3D printing machine which actually generates your medicine overnight, and you take it next morning. Or your VX.
Yes. And could I ask you one other point? It seems as though the German group of nations developed the chemical weapons and the Western group successfully did the nuclear ones. That seems a fairly clear-cut division. Is that so?
Well, of course, the early chemical weapons were produced in the 1930s. Yeah. Before the physicists were driven out to America. Yes. so I think there was a migration of skills. Had the Jewish physicists not been driven out of Germany, then I think Europe might have achieved a double whammy.
Mm-hmm. And if you consider biological weapons, are there the same separations between biology in the different nations?
I honestly don't know. I really don't know. Yeah. It's not,
Yes, John.
I believe the Germans had stockpiles of sarin and taboon in 1944.
Yeah.
Really?
What prevented them from using them? Because they could have swept the D-Day beaches clean.
Yeah.
And saved their empire. If it's...
Yeah, I think... first of all, the country was falling apart at the time. But also there was always this fear of the scorpion turning on you. How do you deliver it? How do you deliver it so that your own troops are not incapacitated?
I believe we were totally unaware of these weapons in the West. Yes. So they would have had the advantage of surprise and the lack of defence.
Yeah, but they might have surprised themselves too.
Point taken, yeah.
My understanding was that they'd been monitoring the phosphate deliveries into the UK, which we'd been using for fertiliser, but because you used phosphate as the basis of the nerve gases, they assumed that we had also got that. And in fact, they'd been testing them out on cows, so we did have some early knowledge of it.
And it was fear of retaliation.
Absolutely, because they thought we'd already stockpiled.
Yeah.
And of course, in Mein Kampf, Hitler wrote he was gassed in World War One.
Yeah.
By mustard gas. He wrote in his diary at the time that he was going to go into politics to stop this horror ever happening again.
Yeah.
And he had actually, according to the reports, stopped the use of chemical weapons to some extent because of what he'd experienced. They were actually too bad for him.
Yeah.
Maybe I could make one more comment. Off the coast of Belfast, about 8 miles off the coast, there are about 1.5 million tons of chemical weapons dumped.
Yeah.
They should have gone deep Atlantic, but sailors were on piecework, so they dropped it very close to the Scottish, Isle of Man and Irish coast.
Yeah.
Because they're underwater, they're not considered to be chemical weapons. Because a chemical weapon is defined as a chemical that can be used as a weapon. Yeah. And the argument goes that
these can't be used
you can't
anymore.
use them, and therefore they're not chemical weapons anymore, which is the sort of thing lawyers love, but of course they're still the same.
Well, let's hope that corrosion sorts it out.
Well, corrosion is sorting it out. I mean, for example, off the coast of Denmark, in the Baltic Sea, 26 trawlermen had to be treated by plastic surgery because they fished up a corroding mustard gas bomb which went off on the deck of their ship. Yeah. So corrosion is going on, but that actually is making them more rather than less dangerous, and there's no obligation to deal with it.
They're more dangerous if they're brought up.
Yes, but of course they bring up by accident. The submarine goes close, they get this. About 15 years ago, 30,000 phosphorus bombs washed up on the coast of Northern Ireland and the Isle of Man, where they'd been deep buried. Well, not so deep, unfortunately. There is a whole issue about how we define the chemical weapon in a useful sense, because that danger isn't going away, and they're not marked on marine maps. So, they don't know where they are precisely.
No.
Now, I know... There's a question. Oh, excellent. Come on. Is there a small prize for this?
No, it's gone.
Oh, all right. There isn't a small prize, no. One last question from me, Peter. I know that over the last 6 months you've put a lot of effort into bringing together the facts and things that have built up this lecture. Are we likely in the next 6 months to see a book appear on this subject?
Well, who knows? Who knows? Yeah.
Now, this is really your last chance to ask a question. Good girl.
Hello, you talked a lot about the negative impacts, but you also presented, that the research actually leads to medicinal benefits. What do you think the biggest positive impact of chemical weapon research in your mind has given from a medicinal benefit as opposed to, a negative one?
Yeah, I think all of them were rather little advantages. They weren't really massive advantages, but I think that anything that can improve the quality of nervous life of a person is to be welcomed. So the ability to delay the onset of neurodegeneration, say, and understanding the processes that contribute to the transfer of information across a synapse contributes to that. It's a long way away from mass pleasure, as it were, but it is glints of good contribution. I don't want to overemphasize it.
Sorry, David.
So in that context, what about the use of acetylcholinesterase insecticides, which are absolutely vital in terms of the protection of crops, particularly in tropical countries.
Yeah. Well, I mean, that comes from understanding the role of acetylcholine, basically. So it's a contribution to good. Yeah. But I think you could probably have understood the action of acetylcholine without resorting to chemical warfare.
Last.
So you touched a little bit on decontamination, things like using hypochlorites.
Yeah.
How important do you think it is to fully understand the actions of these chemical warfare agents in order to ensure that we're getting the best sort of decontamination protocols?
Probably not much at all, really, because they're big, fragile molecules, and if you just hammer away at them, then they just fall apart into other compounds. So it really is sledgehammer stuff. Yeah.
Last question? If not, oh yes, well done.
Would you say that the only way to be in any way morally consistent would be to be a pacifist, rather than make judgments about the...
Sorry, what was the beginning of the...
Would you say the only way to be morally consistent would be to be a pacifist, rather than make judgments about the acceptability of one type of weapon over another?
Well, I think that is one conclusion that one could draw. The problem with pacifism is that it allows evil to flourish elsewhere. So you have to decide whether you will simply not take up a weapon, even though you see horrors going on. And that, I think, is probably morally indefensible on the other side of matters. For example, had we just said, "Okay, Hitler, come in, here's your visa," I mean, that would have led to even worse atrocity.
A valid technique in historical analysis, I think, is to imagine what would have happened if, to do a kind of contrafactual analysis. And I've often wondered what would have happened in 1939 if we hadn't gone to war. Yeah. Would the consequences have been any worse in the long term?
Well, there's vigorous discussion at the moment about what would have happened in 1914 and subsequently had we not gone to that rather stupid war in the First World War, where people, on the whole, didn't know what they were fighting for. And in the Second World War, I think people did know what they were fighting for. And there was a different justification for the Second World War than the First World War. And if you thought, well, let evolution run its course by not doing anything in 1940, then the world would be a seriously troubled place now.
Yes.
You spoke earlier of a theoretical kind of sleepy time, lily of the valley drug that would kill people in their sleep or gently. Do you know of any that was in the process of being developed, or would it be considered as bad if a country did produce that and use that against a military target?
Well, of course, it would be even sneakier than mustard. And really, the point that David made, really, that lily of the valley, I mean, if you sniffed someone who was wearing a perfume, you might think, should I go on sniffing? I think it would be morally reprehensible to work on something that was such a sneaky killer. Yeah, without doubt. But who knows if people are actually doing that? An odorless killer needn't be lily of the valley, of course. It could just be odorless, but nevertheless anesthetic.
My interest, perhaps selfishly, is about the future rather than the past. And I worry that the ability to be able to develop chemical weapons is perhaps now more readily achieved on a minor scale than was in the past. And therefore, the ability of terrorists to get hold of chemical weapons and create destruction is more readily available than would have been in the past.
Yeah, I think that is...
How do we circumnavigate this particular problem? And is our only salvation education rather than the ongoing development of chemical warfare?
Well, governments do track the course of significant chemicals through the system. And if too much of one stuff ends up going to somewhere worrying and is not accounted for, then that is examined seriously. So it's really a question of monitoring the precursors. But as I was saying earlier, that if you are content to build up your stock of VX over 10 years, then little dribbles of stuff are very, very hard to detect. It's worrying. I think it depends upon a Stasi-like observation of one's neighbours.
Following on from that question, has there ever been any kind of chemical attack in the United Kingdom, or has it all been overseas?
I'm not aware of any.
Well, this is really the last chance. Okay. Well, I think I must now thank you, Peter, for the tremendous amount of work that you must have put into this. I know that you've really been working very hard over the last 6 months. You've turned the lecture into something that's opened up a wide sphere of reference to us that we didn't really know about. I think we had half ideas about what had gone on. We didn't really know both the good side of the chemical weapons on the microscopic scale. All we did was worry about the macroscopic effects of chemical weapons. We really are most grateful to you for the effort that you've put into this lecture, and from my point of view, this is the ideal situation for these public lectures. The important thing is that what Peter discovered was from about this subject was mainly from his interaction as an officer on the International Union of Pure and Applied Chemistry. Well, he's given the first lecture of this kind to the British Union of Pure and Applied Chemistry, and we're very, very grateful to you. It's rather special to us. Thank you very much.
Thank you very much.